Welcome to ONT Lab number 2. In ONT Lab number 2, we're actually going to be able to see and hear the results of a quality of service configuration. And we're going to begin by describing the modular quality of service command line interface, the MQC approach to quality of service. Once you master these 3 steps, then you can configure class-based classification, class-based marking, class-based weighted fair queuing, class-based weighted random early detection, low latency queuing, class-based policing, class-based shaping, as well as class-based header compression. This is one of the most fundamental concepts in all of QoS configuration. And after we review the 3 steps of MQC, we're going to illustrate its use by configuring class-based weighted fair queuing and treating different graphics on the same web page differently, literally giving them a different amount of bandwidth. We're going to verify that our class-based weighted fair queuing configuration works as we expected it to, and then we're going to add a voice over IP call to the mix. We're going to see what voice quality sounds like while this web page is loading over a relatively low-speed link, a link running at 128 kilobits per second. We're going to notice that the voice quality is not satisfactory, and to improve that, we are going to enable LLQ, low latency queuing, and finally we're going to see how the voice quality has improved after we have enabled LLQ. But let's get started by reviewing the 3-step MQC, the modular quality of service command line interface process. In the first step of MQC, we create class maps. And Cisco has a recommendation that we not create more than 11 total class maps. After that point, we start to be a little too granular, and normally we need far less than 11 class maps to categorize our traffic. For example, we may have a voice class map, an interactive video class map, a mission-critical class map, a transactional class map, maybe a best effort class map, and we can group applications into those different categories. Once we have created these class maps, in step 2 of MQC, we create a policy map. A policy map allows us to assign a behavioral characteristic to the different class maps we created. For example, give this class map X amount of bandwidth. Maybe give another class map priority treatment. Packets in that class get to go ahead of other types of traffic. Maybe we want to police a class map. In other words, set a bandwidth speed limit for undesirable types of traffic on the network. And once we have created our policy map, it doesn't do anything until we apply it somewhere. Typically, we're going to apply that policy map to an interface. And what we're going to do in this lab, we're going to create a couple of class maps using the class-map command. We're going to create a policy map using the policy-map command, and then we're going to apply that policy map to an interface using the service-policy command. Before we look at the syntax, though, let's consider our topology. In our topology, we have 3 routers, and the bottleneck in this topology is the link between routers R1 and R2. We only have a 128K link between those 2 routers. Therefore, when the web server attached to R2 begins to send packets into R2 across that 128K link over to R1 and up to the PC, which is our vantage point, we're going to have some congestion on that serial 0/0 interface. So what we're going to do is configure a queuing mechanism, specifically class-based weighted fair queuing, and here's how we're going to set it up. The web page that we're going to be loading contains identical graphics. There's a graphic of a sunrise, and it appears twice on this web page. It's the same file size, the graphics just happen to be named differently. What we're going to do, we're going to classify those different graphics into different class maps using NBAR, Network-Based Application Recognition. We're going to look into layer 7. We're going to be able to put the packets for those graphics in different class maps based on the name of the graphics file. And what we're going to do with class-based weighted fair queuing is assign a different amount of bandwidth to each graphic. And we're going to take that policy map that we create and apply that class-based weighted fair queuing policy map to serial 0/0 on router R2. Let's take a look at the syntax we're going to use to set this up. In step 1 of MQC, the first thing we do is we create a class map. In fact, we're going to create 2 class maps in this lab. We're going to say in global configuration mode, class-map, and give a name of that class map. Once we're in class map configuration mode, we can use various match criteria to classify which packets belong in this specific class map. And after we create our two class maps, we are then going to move on to step 2 of MQC, which is creating a policy map. We do that with the command policy-map followed by the name of the policy map. But we don't actually do much from policy map configuration mode. The real magic of MQC happens inside of policy map class configuration mode. We say class, give the name of one of the class maps we've created. That takes us into policy map class configuration mode. From this mode, we can turn on a wide variety of quality of service mechanisms. What we're going to do now, though, is we're going to use the bandwidth command followed by a bandwidth amount in kilobits per second. What this bandwidth command says is if the traffic in this particular class needs this much bandwidth that we're specifying, it can have it. And if more bandwidth happens to be available and the traffic in this class needs more bandwidth, then it can certainly use some of that extra bandwidth. But if the traffic does not need all of the bandwidth that we are allocating with this command, it does not use all of that bandwidth. That extra bandwidth becomes available for other class maps to use. Then after we've completed step 2 of MQC and configured our policy map, we're then going to take that policy map and apply it to an interface. Specifically, interface serial 0/0 on router R2. Let's begin our configuration by taking a look at the web page that has those two Sunrise graphics that I was referring to. On this web page, notice that there are two graphics of a sunrise. These graphics are actually the same file, just a copy of the same file with different names. If we take a look at the source of this HTML code, you'll notice one of the graphics is called High Priority JPEG, while the other graphic is called Low Priority JPEG. What we want to do is to recognize and classify these graphics based on their name. If we reload this web page, you're going to notice that these graphics load at approximately the same rate. They're loading over that 128 kilobit per second link. What we should do now is go into our router 2 specifically, and go through the 3 steps of MQC. In the first step of MQC, we configure class maps. Let's create a class map, and let's name it Web High. This is going to match the sunrise on the left-hand side. We want to match a particular protocol. And by the way, when we say match protocol, we are using NBAR, Network-Based Application Recognition. And notice the many different application signatures that NBAR can recognize. What we are specifically interested in is HTTP, but not just any HTTP. We're looking for a specific URL. We are looking for the word high, H-I-G-H, somewhere in that URL. In other words, the name of that graphic on the left that was named High Priority JPEG, it would be matched by this match statement. And the stars are acting as wildcards. We're saying if the word high appears anywhere at all within this URL string, we're going to be matching it. And the lettering H-I-G-H, that is case sensitive. Let's create another class map. Let's create a class map this time called Web Low. This is going to match our low priority sunrise. We're saying match protocol HTTP URL, and then in quotes, we say star, low, star, close quote. That's step 1 of MQC. Step 2 of MQC is to create a policy map. Let's create a policy map named Web. Not much happens from policy map configuration mode. As we mentioned earlier, the real magic of MQC happens in policy map class configuration mode. Let's go into policy map class configuration mode for the class called Web High. And for this class, let's give it 24 kilobits per second of bandwidth. 24 kilobits per second of bandwidth can be given with the command bandwidth 24. Let's go into policy map class configuration mode for the Web Low class map, and let's give it only 1/3 as much bandwidth. Let's say bandwidth 8. And by the way, when I say this, are we actually only going to give 24K of bandwidth to the sunrise on the left and 8K to the sunrise on the right? No, if extra bandwidth is available, Class-based weighted fair queuing allows us to use that extra bandwidth. However, the ratios, the 3-to-1 ratio, will stay the same. That's step 2 of MQC. In the final and third step of MQC, we go into interface configuration mode for interface serial 0/0, and we're going to say service hyphen policy output web. In other words, as traffic exits serial 0/0, the web policy map, which is giving different amounts of bandwidth to those different graphics, is going to be applied. And we're told that Cisco Express forwarding is a requirement when we're using NBAR. No problem. Let's go out to global configuration mode and turn on CEF, Cisco Express Forwarding. We do that with the command IP space CEF, CEF. Now let's go back into interface configuration mode for interface serial 0/0 and once again say service hyphen policy output web. And recall that weighted fair queuing is a default on slow speed interfaces. We need to turn that off. Let's say no fair-q. Give the command once more. This time it accepts it. And I think we are done now with our class-based weighted fair queuing configuration. Let's go back out to our web page and verify the behavior. If we open up the web page once again and do a reload, notice the results. The graphic on the left-hand side is loading at about 3 times the rate of the graphic on the right-hand side. This is visual evidence that class-based weighted fair queuing is doing its job. We're giving 3 times as much bandwidth to one graphic versus another graphic. Now imagine the graphic used in this example was representative of your mission-critical traffic, maybe your e-commerce traffic. Using a class-based weighted fair queuing, you can give extra bandwidth to the applications in your network that matter most. Let's go back and revisit our topology once more. As we take a look at our topology, let's visualize what just happened. As packets are coming from the web server for those 2 different graphics, we are giving 3 times as much bandwidth to one graphic versus another graphic. And we were viewing that from the perspective of the PC that you see on screen. But also notice that this is a voice over IP topology. We have a couple of analog phones plugged into foreign exchange station ports in R1 and R3. Let's see what the voice quality is across this network. Let's place a voice call. I'm picking up the handset for extension 2222 and I'm dialing 1111. We can hear that phone ringing. I go off hook. We now have a phone call in progress across this network. And right now, there is no web traffic. The 128K link between R1 and R2 should be more than sufficient to carry this voice over IP phone call. And here's a great way to test voice over IP phone quality. Instead of just having someone talk to you and you judge the voice quality, if you want to detect if there are any breakups in the voice, you may want to have the person at the far end hold down one of the keys on the touch tone keypad, and you listen for a nice solid tone on your end. That's what we're going to do. I'm going to hold the handset for extension 1111 up to the microphone, and I'm going to press down one of the keypad keys on extension 2222, and let's make sure that we have a nice solid tone. That sounded like a nice, solid tone. It did not sound like we were dropping packets or breaking up. However, let's reload that web page, and now with data traffic going across that link at the same time that we have phone traffic, let's see what the voice quality sounds like. Believe it or not, I was holding down the button just then, and I did not hear any tone whatsoever get through. The voice is being completely starved out by the data traffic. I think what we might need to do now is to tell the router, to tell R2 to give very high priority treatment to voice traffic. Let's take a look at the syntax that will allow us to do that. And by the way, when we do this, we are configuring something called LLQ, low latency queuing. It works almost identical to class-based weighted fair queuing, except we can go into policy map class configuration mode for one or more class maps and specify that we want the traffic from those class maps to go into the priority queue. The priority queue gets emptied first. Packets in that queue get to go ahead of other traffic up to a point. We're not going to starve out the other traffic. So when we give the command, for example, priority 64, we are saying that we can send traffic from the priority queue at a rate of 64 kilobits per second, and those packets get to go first. But if we try to take more than our allotment of bandwidth, if we try to take more than 64 kilobits per second, we will be policed, we will be limited. And the reason for that is we do not want priority traffic to starve out our non-priority traffic. However, in our example, if we go in and say priority 64, based on the codec we're using G.729, that should be more than enough bandwidth to accommodate that voice call. Let's go out to R2 and set this up. On router R2, we're wanting to turn on low latency queuing so that we can give high priority treatment to our voice traffic. To do that, let's go back into global configuration mode and create a class map that can recognize voice traffic. Let's create a class map called voice. How are we going to recognize voice traffic? Let's use NBAR, Network-Based Application Recognition. To do that, we can say match protocol RTP. However, the challenge is some networks have streaming video as well, and streaming video also uses RTP. But if we give some context-sensitive help, notice that we can specify that we wish to match audio RTP packets. These are our voice over IP packets. So we will say match protocol RTP audio. And for step 2 of MQC, we have already created a policy map. Let's just go back into policy map configuration mode. We had a policy map that was named web. Let's go into policy map class configuration mode for the newly created voice class and give the priority keyword. Let's say priority 64. In other words, I want my voice traffic to go ahead of other traffic up to but not exceeding a rate of 64 kilobits per second. No need to do the third step of MQC because we've already done it. We have already applied the policy map named web to interface serial 0/0 in the outbound direction. Let's go back and once again take a look at our topology so we can visualize what's happening and see if our voice quality has improved. As we take a look at our topology, realize that we have now applied low latency queuing to interface serial 0/0 of router R2. Now we are instructing router R2 to give high priority treatment to our voice packets. We still have the phone call in progress from before. Let me in the background reload that web page and once again hold the handset for extension 1111 up to the microphone while I hold a keypad button down on extension 2222, and let's judge the voice quality. Remember, previously when we did this, we heard no audio whatsoever. It was being completely starved out by the data traffic. I am now reloading that web page in the background. Let me hold up the handset for 1111 to the microphone while I press a key on 2222. I suppose the good news is we at least heard a tone this time, but it still wasn't of acceptable quality, was it? It still wasn't a nice, solid tone. How could that be? We correctly configured low latency queuing. Why were we still getting gaps in that tone? What was happening is not the fault of low latency queuing. We were not hearing packets being dropped just then. What we were hearing were packets being delayed. We were hearing the result of serialization delay. Serialization delay results when we have a big data packet trying to get out of a relatively slow speed interface, like our big web packets in this case. They're trying to go out of this 128 kilobit per second interface, and it is taking so long for them to get out of the interface that they are delaying our voice packets. Remember, the voice packets let the data packets take a turn. We're not trying to starve out the data packets. So we have made progress at this point. We now at least hear the audio. We're giving it priority treatment, but because the link speed is so low, we are experiencing excessive serialization delay. We are going to fix this issue in ONT lab number 4 when we configure multi-link PPP. But for now, let's wrap up and review what we have seen in this lab. In this lab, we began by reviewing the 3-step MQC process. Step 1, create class maps. Step 2, create a policy map. Step 3, apply that policy map. And one of the many QoS mechanisms that we can configure using the three-step MQC process is class-based weighted fair queuing. We configured class-based weighted fair queuing, CBWFQ, to give different amounts of bandwidth to different graphics inside of a web page. We verified that behavior by watching the web page load. Remember, the sunrise on the left loaded at about 3 times the rate as compared to the sunrise on the right? And then we placed a voice over IP phone call across this topology, and while that web page was loading, it completely starved out our voice packets. We did not hear any voice whatsoever getting through. To help remedy that situation, we configured low latency queuing. We did that with the priority command, and after we did, we listened to the audio quality again, and it was better. We could hear the tone, but we were still experiencing gaps in that tone. And we made the observation that those gaps were not due to dropped packets. Those gaps were due to delayed packets. This is an issue that we're going to revisit in ONT Lab number 4 when we configure Multilink PPP.